Right, so here we're going to solve radical equations, specifically square roots. So I'm going to start with these three real basic equations so that we can kind of see what's happening, and then as we move to bigger equations to solve, we can anticipate what we might see and be careful of what might happen when we're solving them, just so we can anticipate certain responses, certain answers, and if they make sense or not. So if I wanted to solve these, right, just like I normally would approach this, there's only one x in the equation, so I should just be able to undo order of operations to get them by himself, right? We know that a square root can be canceled by squaring, and as long as I do something to both sides of the equation, I can manipulate the equation as often as I would like. So in this case, I have to square the entire side, so there's not much going on each side. So if I square each side, the square and the square root would cancel to leave us with just x. 4 squared, 4 times 4 is 16, right? Now, we got to be careful because as a square root function, right, ignoring the 4, I mean, I can plug in any x that I want in here, of course, but the square root doesn't always work for any number that I have for x, right? 0 works, positive numbers work, but negative numbers, right, square root of negative numbers are imaginary. So if I happen upon a value, then I need to make sure that the value underneath the root isn't going to be negative, because then that'll bring upon imaginary numbers, and imaginary numbers don't, make the left side necessarily equal the right side, especially if I have like a real number like -4. So since we know that square root functions have a restriction on the domain of x's, we're going to want to check our answers here, right? I mean, it could just be just looking at it real quick, right? Square root of 16 is 4, so this one's looking pretty good, right? Or if it's more complicated, we can write it out. Okay, so in this case, same idea. I need to get rid of the square root, right? The entire function over here, if I square it, then the square and the square root would cancel, but that means I have to square this side. So the square and the square root leave us with just x. -4 squared is -4 times -4, which is positive 16, right? So mathematically, when I solve this down, this is what I get. But for it to be a real solution, I would need to plug it in, and it would actually have to make the left side equal the right side. So if I look at this one, right, the square root of 16 needs to be equal to -4. So when we're doing these, we're always going to plug them back into the original function, not any of the prior steps below it, right? Always the original one. Now, we know that square root of 16 is 4, and 4 does not equal -4, so that means that 16 isn't really a solution. So when we're solving an equation and we get a solution, right, these are all the feasible solutions for this equation, right? Mathematically, if any number was going to work, 16 would be that number. But when we plug it in, we can see that it does not work. So what we call this is an extraneous solution, right? Extraneous solution. Meaning it's a solution that we get from algebraic manipulation, but it's not going to actually solve the equation, which means it's not really an answer. So 16 was the only feasible answer, but we checked it and it doesn't work. So in this case, there would be no solution. Solution. Right? Okay. Now, if we wanted to do this, what I'm going to suggest is trying to get that root on its own. Because if we're going to remove a root with a square, we really want the root to be the only thing on that side. So this is a negative. We can think of this as a -1 times the root, which means we can divide both sides by -1. That'll give us the square root of x to be +4 again. And then if we square this thing, right? We're kind of back over here, where x equals 4 squared is 16, right? If we wanted to check this, right, remember, plugging it back into the original one, not this guy here. So if I check it, the opposite of the square root of 16 should be equal to negative 4. We know that the square root of 16 is 4, but then the opposite of 4 is negative 4, which does actually work out to be true. So this guy is actually the solution here. So in this case, 16 worked, right? This case, we had no solution. This case, 16 also worked, right? And what I want to do is I just want to look at the graphs of these things just to kind of make sense of like why some of the negatives work and some of the negatives don't work, okay? So it's not necessarily that x has to be greater than 0, right? I mean, we can see that when we plug it in, 16 was greater than 0, but we do want to make sure that the equation actually holds true. So if I were to look at these two sides of the equation as different functions, like f of x and g of x, then f of x is a square root function, which looks like this guy, if you were to graph it. And then g of x being 4, y equals 4 is just a horizontal line. So you can't really see it on this graph, but it's eventually going to come up here and cross this line. It'll take x to be 16 before we can come up here and make that happen. This one we saw had no solution, right? Again, if I graphed square root of x against negative 4 is actually down here, so it's a horizontal line here at negative 4, and this guy is going to grow continuously, so it's never actually going to come down here and approach this line, which is why it had no solution, right? Or 16 being an extraneous solution, which didn't really work. Now, in terms of the graph, this guy has this shape, but this negative 1 is going to reflect it. So even though negative 4 is down here, if I reflect it over, it will again eventually come down here and cross, which is why this guy, this 16, actually made an equation hold true, right? So we don't really want to consider the graphs every time, right? I mean, we can see why things work and things don't work. So that's why, we know square roots have a restriction on the domain. So when we get these x's, which is our domain values, we want to check to see if that one kind of meets the criteria, right? And if not, then we will just ignore it as the only possible solution, which means we would either have no solution or if it doesn't work, maybe we have two solutions that we need to try. It kind of depends on what we have. Okay, so let's give one a try. I'm not going to look at the graphs. We're going to keep some of these things in mind as we move along, right? Okay, so remember, we have a square root, right? That's a concern to us. There's only one x, so I should be able to just get him alone by removing operations. Now, I know that to remove a square root is going to require squaring the square root, but in terms of the equation, I would have to square the entire side, right? I can't square like individual terms on each side, right? It doesn't work that way, right? I mean, if you really want to think about it, right, we have two different terms, right? We know that we would have to square the entire side of the equation, but to square each piece individually would be assuming that we could distribute the square to both pieces, which doesn't really work out, right? If we're going to square this entire thing, it's not going to work out like this. It would be like two of them foiled out if we want to distribute it and collect it, which, I mean, this is legal, right? I don't know if it's going to help us get rid of the square root and get the x isolated. So the best thing we can do is to not have two terms here. If we just get the term with the square root on his own, then we don't have to worry about this. So this 4, he's got to go, right? So if we subtract him from both sides, then we'll be left with x plus 3, right? 5 minus 4 is 1. And now that the root is on his own, if we square both sides, then the square root is going to cancel, right? 1 squared, of course, is 1. And now that the root is gone, we can proceed, right, Subtract 3 from both sides, x equals negative 2. But remember, square roots have restrictions on the domain, so we want to check our answer. Always check it into the original one, not this guy, the original one. So I'm going to take this guy here. Let's check it out. All right, the square root of x, which we said was negative 2, plus 3, plus 4, should equal 5. So what do we got? Negative 2 plus 3 is 1. Right? Square root of 1 is 1, and 1 plus 4 does equal 5. So this is a real solution. And it's the only feasible solution because that's what we got, so we know there's no other ones available. Right? All right, let's try another one. Okay. So, see 1x, solving for x, right? Now there's only one of them. It's under the square root. I know if I'm going to get rid of the square root, I need the square alone, right? Otherwise, if I square the whole side, there's a lot of other things going on here. I definitely don't want to deal with that. Now, don't be tempted to do 5 minus 3, because remember, this is 3 times the root. We would have to do multiplication first. So this is the term with the x. That means he's got to go. So if I subtract 5 from both sides, right, I'll still be left with the negative 3, right, because the 5 is positive, the 3 is negative. Right? Negative 1 and negative 5 is negative 6. Okay. Now you might say, well, square roots can't produce negative numbers. Well, that's not necessarily true, right? X can be anything, right? The thing underneath the root can't be negative. But let's not worry about that, right? When we get to the end here, we'll check to make sure that things are working out. Okay? Because it's not that we can't have outputs when we plug x into a function to produce a negative, because we got a lot of other operations going on here. So we can undo this multiplication again with division. Right? That's going to leave me with the root. Negative divided by negative is positive 2, right? Now that the root is alone, if I square both sides, the root will go away. So we just have x plus 2. 2 squared is 4, right? And then we can just subtract the 2. So x has got to be equal to 2. That's the only feasible solution. But, like I said, we're going to check it, right, into the original. Right, into the original. So, let's check it out. I mean, if you can do it in your head, I mean, by all means, I'm just going to write it out just so we're following along. So, x is 2. All right, so I'm going to plug that in here. So we got 5 minus 3, again doing order of operations. 2 plus 2 is 4, but the square root of 4 is 2. So all of this is 2, still times 3. So 5 minus 3 times 2 is 6, so 5 minus 6 is negative 1. Yeah, that's true. So 2 is the real solution that works there. Right? All right, let's try another one here. Okay, so I mean, there's 2 x's. I know eventually I'm going to want to put these 2 x's together if I'm going to try to isolate and get like x equals just a number. But for the time being, the root is my priority. I can't put these x's together because one's under a root and one's not. So if I am going to try to put these together, I definitely have to get rid of the root first. The root is the only thing on this side, so I can square both sides, and the root and the square would cancel, which is good. So I'll be left with what? 10x minus 24. Over here, x squared is just x squared, right? Not much going on here. Okay, so no more root. Now I can kind of look at this more broadly here. I got 2 x's. I want to try to put them together, but I can't add x squareds and x's. I mean, I can move them to the same side, but I can't add x squareds and x's. So if I have multiple x's that can't be put together, I know some sort of factoring is going to need to take place, right? And if I want a factor to make this useful, I'm going to need everything on one side equal to 0. So I like to leave the larger degree term positive, so I'm just going to subtract the 10x from both sides and then add the 24 to both sides. So we have nothing on the left now, right? The x squared, I'm just going to put them in order, right, from largest degree down, right? So now I'm ready to factor. I got it equal to 0. That means if this thing factors down, I can use 0 to my advantage, right? Now, whichever factoring method you want to do is fine. I'm just going to do like an old guess and check method. I know 3-termed expressions can multiply to 2 binomials. I know the only way to make x squared is x times x. And these two have to multiply to 24. So I need multiples of 24, which are what? 1 and 24, 2 and 12. What do we got? 3 and 8. 8, 16, 24. 4 and 6. I think that's it. So as long as my coefficient is 1, I mean, these two are the same, it doesn't really matter which one I put here and here. I just need them to add to negative 10. Right? Now I can make negative 10 from negative 12 plus 2. Right? Negative 12 plus 2 would make negative 10. But remember, they also have to multiply to make 24. And a positive times a negative would make a negative 24, so that can't be it. But I can do negative 6 and negative 4, because negative times negative makes a positive. So this is going to be negative 4, negative 6. Right? If you need a refresher on factoring, I made other videos if you want to go back and watch them on guess check method. You could also do the AC method, right? Whatever method you like here. But nonetheless, these are both equal to 0, and as a product to be equal to 0, this guy being 0 means x would need to be 4, and this guy would be x equals 6. So I have 2 possible solutions. Now, I do need to check them because, like we said, roots have restrictions on the domain, so I need to check them both. Okay, so here we go. I'll start with 4. So we got the square root of 10 times 4 minus 24, and then minus x, which is 4. I got to plug in 4 into both places. Let's see, so what do we got? 10 times 4 is 40. 40 minus 24, what's that, 16? So square root of 16 equals 4? Yeah, square root of 16 is 4, so that works, right? So let's try 6. So again, plugging it into the original, this is 10 times 6 minus 24 equals x, right? Not 4, because x was 4, so equals 6, right? So what do we got? 10 times 6 is 60 minus 24. 60 minus 24, what's that, 36? And square root of 36 is 6, so yeah, they both work. So 2 solutions here. 2 solutions. Okay. Now, it could be that one works and one doesn't. So we would say, oh, that guy don't work, so maybe just this guy. But we do need to check them both. They both could work, they both could not work. One could work, not the other one. So just be careful. Okay? All right, let's see what we got. Let's try this one. Okay. All right, so again, I got 2 x's. That's okay, right? I need to get him alone, but he's underneath the root. In order to get rid of the root, I need the root alone. So the 6, he's hanging out with the root. I don't want him. So I'm going to add the 6 to both sides, right? Remember, priority number 1 is getting this x out of the root, and then we can deal with how he's going to go together with that other one, right? So that isolates the root. That's good. 15. X plus 6, I can't put them together, but that's okay. Now that the root is isolated, if I square both sides, the root and the square would cancel, right? So that would give me 2x plus 15 over here. Now over here, we can't distribute the square on 2 terms, right? This would be the same as saying x plus 6 times itself 2 times. I mean, that's what an exponent means, right? So I would have to distribute, right? So nothing going on over here, just 2x plus 15, right? If I distribute x times x is x squared, x times 6 is 6x. Then I'll distribute the 6. That's 6x as well. 6 times 6 is 36. Okay. So, not much going on. I'll just leave him for now. I'm just going to clean this up a little bit. X squared, 6x and 6x makes 12x's. Right? So I just cleaned up the right side a little. Right? I still have a whole bunch of x's. I know I can't add x squareds and x's together, so I know I'm going to need to factor again. So again, I want to put everything on one side. I'm going to leave this x squared alone. I'm going to move him over here, and I'm going to move him over here. Right? That leaves us with nothing on the left. I got my x squared, my largest degree term positive. That's what I like to do. You don't have to do that if you don't want to. 12 minus 2 is positive 10. 36 minus 15. What do we got? Positive 21. Okay. All right, cleaned it all up. I do have to factor. Right, I'm going to use guess check again. Again, you can factor this however you want. The only way to make x squared is x and x. 21 is 1 times 21, or 3 times 7. As long as the 3 and the 7 are positive, then we can make 10, and then positive times positive makes a positive 21. Right? So that means that this guy, still equal to 0, would have to be 0, would make 0 if x was negative 3, and this guy would make 0 if x was negative 7. Right? So now that we have our feasible solutions, right, we need to check them. Remember, back into the original one, way back up here, original one. Okay? All right. So I'll check the negative 3 first. So what do we got? 2 times negative 3 plus 15, still under the square root, minus 6 equals x, but x was negative 3, right? Okay. So, 2 times negative 3 is negative 6. Negative 6 plus 15. Right? Still got the minus 6 out here, right? But we'll do order of operations first. So negative 6 plus 15, what's that? 9. So square root of 9 is 3. 3 minus 6 is supposed to be negative 3, which it is. So that works. Good. All right, let's try negative 7. So 2 times x, which is negative 7, right? 2 times x, plus 15, that's under the root, minus 6 needs to be equal to x, right, which is negative 7. Okay, just make sure you put the x's in all the places. Right? It's very common to put the 3 here because, we thought it was equal to negative 3. So, what do we got? 2 times negative 7 is negative 14 plus 15. Still got the minus 6. So, what's that? 1. Square root of 1 minus 6 is negative 7. 1 minus 6 is not negative 7. So, this don't work. So, negative 7 is not a solution, but negative 3 did work. So, only negative 3. Right? This was an extraneous solution. So, we don't like it. So you might be asked to find extraneous solutions, right? That would be it. You can say this is an extraneous solution. This is, a real solution, right? Depending on, what you're asked to do here. Right? But that's why we got to check both of them. All right. Let's try one more. Okay. All right. Now, we got 2 roots. They both got an x under them. So we definitely don't want either of these roots, right? Now, there's a couple of different ways we can approach this, but I'm going to approach it in a way that keeps all the terms small, right? So, realistically, as long as you do proper operations on both sides of the equation, you might be able to get to the answer a different way, okay? I'm going to go with the idea that in order for a root to be removed, if it was the only thing on this side of the equation, then squaring it would cancel that root. Now, I can't get both of these roots alone at the same time, right? Because if I wanted to get him alone, I'd have to move him over here by adding, but the 1 is over here. So I would have 1 and the root, right? Same thing here. If I wanted to get him alone, then I'd have to move him over here. So one of these roots is going to go with the 1, and the other one can be isolated. So we're just going to take care of them one at a time. Now, I tend to feel that negative signs throw people off. So if I had to choose which one I'm going to move this right one, right? Because it's minus this entire root. So if I added the entire root to both sides, then a positive version of the root and a minus version of the root would cancel each other out, right? So I can move the whole root over. That's going to get this guy alone, right? He's the only thing left on this side. I still have the 1, so it's still 1 plus this entire thing, right? But at least this one's alone. So now if I square both sides, right, this cancels out, and we're just left with, oops, not 2x plus 2, 2x minus 3, right? Now this side is the issue because, again, I can't distribute the square. If that was the case, then this square would just cancel, and life would be pretty good here. But remember, this is 2 different terms. So this whole expression raised to the 2 means that expression times itself 2 times, right? So if we think about it, these are 2 binomials, right? So I want to distribute this guy and distribute this guy. And that will take care of this multiplication, right? This guy's going to go along for the ride because I definitely don't want all this going on because I need to get to that other root. He's good. No more root. He's just hanging out. We need to take care of this side. Okay, so just, 2x minus 3. So let's distribute. 1 times 1 is 1, and 1 times the root would be 1 root, right? So just x minus 2. If I distribute this one, 1 times the root is just 1 root, so plus x minus 2. And then the root times the root, I mean, these are identical terms, so if I want to think about it, that would be the root times the root is the root squared, right? If I'm multiplying the same thing twice, then that's what a square is, and the square and the square root would cancel. So when I distribute, this is just going to be, it's going to be positive, right? Positive times positive is a positive. It's going to be a positive version of the x minus 2, right? Because the square roots cancel. Okay, so not that it's looking any nicer, but at least we don't have it grouped up, right? We distributed it out. Now, these 2 roots are identical, right? And if I'm adding roots together, as long as they're the same, then I can just add the coefficients together, because the coefficient is the quantity of them, right? So, I got the 2x minus 3, right? I can actually put together this negative 2 and this 1, right? And then I still have this x. So I'm going to write the x first, because he's just, hanging out, just x. 1 minus 2 is negative 1. And then 1 of the roots plus 1 of the roots would be 2 of the roots, right? So as long as the roots are identical, then I can just add as a quantity, okay? So I have a root. I don't want him. I have other x's, but we'll deal with those later. I need to get this root alone so that I can square it and remove it, right? But these other terms that aren't under the root, we can push them to the other side and kind of collect them over here, right? We can subtract x from both sides, add 1 to both sides, right? So 2x minus x is just x. Negative 3 and 1, right, is negative 2. Now I still got this 2, so it's still 2 times the root, right? Now here we have some options, right? If you're saying, oh, well, the root's almost alone, I can divide by 2, that means I would divide both sides by 2. Now, not that that's a big issue, but if I did divide by 2 over here, this would reduce down, right? 2 divided by 2 is 1, but here it'd be x over 2 or 1/2 x. Now, if you don't want to deal with fractions, right, I would suggest not dividing this away, right? Technically, the root is isolated because with multiplication, if we squared both sides, right, we can actually, as long as it's two multiples, right, as long as it's two multiples, right, we got this multiple and this multiple, right? We couldn't distribute the square here because it was two different terms added together, but this is all one term. So this 2 could actually be distributed to each multiple of this same term here. Now, this guy over here, again, we have to FOIL him out. So I'm going to say this is, x minus 2, x minus 2, because this is two different terms. But this would be 2 squared, right, which is 4. And then the square root squared, kind of like we did over here, the square root squared is just x minus 2. Right, but remember that it's still multiplication. So it's this guy times this guy. So it's going to be 4 times x minus 2. Okay, don't put a plus here, right, because this is multiplication. This is all one term. But at least this keeps, it's going to make the numbers bigger because I'm squaring the 2 instead of dividing it away. But at least I won't have fractions, right? Because if I had a 1/2 x over here, and then squared it, now I'm FOILing this out with these halves, and I don't really want to do that if I don't have to, right? Okay, so let's distribute x times x, x squared, x times negative 2, negative 2 times x, negative 2 times negative 2. And then over here, I'm going to distribute this guy as well, so 4 times x and 4 times negative 2, right? All right. Taking a while, but at least we're whittling things away. We have a whole bunch of x's. Not all of them are going to go together. So I'm going to try to move them all to the same side. Right? I'll go ahead and put these two together while I'm at it. So these make what? Negative 4x's. Okay. Now I'll move everything over. I'm going to keep this x squared positive. So I'm going to pull this 4x over. And I'm going to pull this. I got to add 8. 8 over, right? Okay, so x squared minus 8x plus 12 equals 0. All right, on the home stretch. We still got a factor. That's all right. 3 terms. Can factor down into 2 binomials, right? It's got to be x and x. Multiples of 12. What do we got? 1 and 12, 2 and 6, right? I can make 8 from 2 and 6, right? As long as they're both negative. And a negative times negative makes a positive, so negative 2 and negative 6. That means that x would be equal to positive 2. X would be equal to positive 6 to make 0, right? All right, we did it. But remember, these things started off with a root, so unfortunately, we got to check them. Now, we're checking them way back up at the top, right? So I'll just jot it down over here, okay? But let's remember what it started off as. Okay, so remember, x is 2. I'm going to plug in 2 first. So 2 times 2 minus 3 minus 2 minus 2 equals 1, right? All right, I'm done with this. I'll come back down here. Okay. 2 times 2 is 4. 4 minus 3 is 1. Right? 2 minus 2 is 0. So, square root of 1 is 1. Square root of 0 is 0. 1 minus 0 is 1. That is true. So, 2 works. Right? All right, let's plug the 6 in. I'll plug it in where these x's were here. So, 2 times x, which was 6, minus 3 minus x minus 2, right? So 2 times 6 is 12. 12 minus 3 is what, 9? 6 minus 2 is 4. Square root of 4 is 2. Square root of 9 is 3. 3 minus 2 equals 1. That's also true. So both of them are actually real solutions here, right? So, man, a lot going on here, right? So let me just recap this one. A lot going on. So remember, at the very beginning, how many x's do we see? We see 2 different x's. We definitely want to put them together if we're going to try to get x alone, but each one is underneath its own square root. And that's a problem, especially because we can't isolate both roots at the same time, right? If it was just this root equals this root, then if we squared both sides, they'd both go away. Man, that would have made things a lot less complicated. But there's no way to deny that both roots can't be isolated at the same time. So I just picked one. Move the one root over, isolate him. If we square him, he's gone. If we square this side, we got to kind of whittle it away, right? But 1 down, 1 to go type of scenario here, right? Now we want to get this root alone. We shoveled everything over to the left. Technically, he's alone, even though there's a 2 here. If both of these terms were divisible by 2, I would have just divided by 2. Let's make everything smaller. But since it wasn't, I chose to not go with fractions. So if I square it, now we have no roots, business as usual, a lot of x's that don't go together. So I need to put them all on one side so that I can factor. Your choice of factoring. Remember, we started off with roots, so we need to check these answers. Right? All right. Hope that helped.